All right, welcome back again, everyone. Today we're doing section 16.7, which is all about surface integrals. And this is kind of an exciting one because we get to talk about flux and things like that. And it's going to set us up for Stokes' theorem and the divergence theorem, which we're going to get in the last two sections. So this is a really fun section. I hope you enjoy it. Let me pull up the slides and we'll get started. There's just a lot of beautiful mathematics at this point. Okay. All right, so here's the overview. We're just going to develop the idea of a surface integral, develop the mechanics and all that kind of stuff. It's going to be a repeat of things we've seen in the past, so I apologize if that's boring. Then we'll talk about surface integrals of scalar functions of three variables. We will very quickly address the physics applications that we saw in previous lectures, just updating it to deal with surfaces. That's pretty much it. We'll do surface integrals of graphs of two variable functions. So graphs that are basically of the form z equals f of x, y, x comma y. We're going to talk about orientable surfaces because we need to be able to orient our surfaces in order to talk about flux. Then at the end, we'll talk about surface integrals of vector fields, which is basically telling us the flux, which is kind of like how fast stuff is passing through a surface. And then we'll finish up with a brief talk about electrostatics and heat flow, which you will see in much, much more detail in your engineering classes. All right, so here is the development. If you remember earlier, I mean, hopefully you do, we learned how to compute integrals over paths, right? Those were line integrals. Surface integrals are basically the exact same thing, except now we're taking the integral over a surface in space instead of taking it over a curve in space. So intuitively, let's say we have a surface in R3. We want to evaluate a function on just that surface, and then we want to integrate those results. That's basically what we're going to do. We're going to adapt the mechanics of the Riemann integral again to allow us to integrate scalar functions and vector functions over a surface. But again, the construction is virtually identical to what we saw in the very last section, the one, section 16.6. And in fact, just like with a path integral, you can really think of a surface integral as like a weighted surface area. And you're going to see that. It's basically like tagging every point on the surface with a particular weight and then adding up those weights. That's essentially what's happening here. We're going to do it for scalar functions first, and then we'll do it for vector functions about halfway through or so. So here's the development. Hopefully this is all review at this point. Suppose we have a smooth surface S, and we're going to say it's determined by this vector equation, given like so. We studied these in the last section. We're just going to assume for ease that our parameter domain is a rectangle, and same deal, same run through every single time. Divide D into subrectangles, R sub ij, with dimensions delta U and delta V. Then the surface S is divided into corresponding patches, right? Remember, it's like a quilt, and you're going to cut it up into patches. And the area of each one of those patches is given by delta S sub ij, right? That's the basic idea. Now, choose any sample point, P sub ij star, in each patch, any sample point you'd like. Evaluate your function f, your scalar function f, at that point. Do that in each patch. Multiply by the area delta S sub ij, and then you can form the Riemann sum like so. This is essentially an approximation of the exact value of the integral right here. So pretty much the same structure. And again, you can kind of see what's going to happen next, taking the limit, refining the partition, and we produce our surface integral. So this is the definition of a surface integral with respect to surface area. So if f is a scalar field defined on a smooth surface S given by the vector function r of u comma v, where r of u comma v is in this rectangle, AB cross CD, then the surface integral of f over S with respect to surface area is this integral here. There we go. And it is the limit of this Riemann sum. So same construction as before. Notice now we're differentiating with respect to S. So with respect to the surface area, that's what this ds is standing for. All right. One thing to notice is notice the similarity that it has to a line integral, right? Remember when we had a line integral, it was, for example, f of x comma y, and this was d little s, right? Because we were integrating with respect to arc length. Now we're integrating with respect to surface area. but the construction of the line integral was very, very similar to this, very similar to this. Um, Now, in order to actually evaluate the integral, it helps if we can represent it or re-express it in terms of the parameter domain, right? So for each one of the patches, we're going to use approximating parallelograms in the tangent plane. And we're going to do that for each one of the patches. So if you remember from the last lecture and lecture 15.9, frankly, the area of that patch can be approximated by the area of that parallelogram that's determined by the tangent vectors at a given point, right? So RU and RV are tangent vectors. Those form the corner of a parallelogram. There you go. You kind of see it there. So we can approximate the area of the patch using the area of those parallelograms, and we can re-express our sum like so. So now this delta S sub ij, the area of the patch, is approximated with the area of these parallelograms, and we get the following corollary after taking the limit and making the partition more refined. So say our vector function is C1, where R sub u and R sub v are non-zero and non-parallel in the interior of D, then the surface integral of f over the surface S with respect to area is this. So now we're integrating with respect to the area of the parameter domain, not the area, not the surface area of the thing itself. Oop, oop, oh no, is my camera freaking out? Maybe. It's getting old. Okay. um, Anyway, so this should look pretty familiar. Yeah, if you look at the structure, this is really just the change of variables formula again, right? So section 15.9 popping up again and again and again. This is literally plugging in your change of variable, literally plugging it in. You're evaluating f at this parameterization. This is going to be the like absolute value of your Jacobian determinant. That's basically what that is. And then there's your area form with respect to the parameter domain. That's it. Now, what's also cool is this. Notice that if you take your function f, your scalar function f, to just be the unit function, the function 1, then what happens is this just becomes 1, and you're left with this, which is the area formula, right? So this is the area formula that we got in the previous section. And this just really emphasizes that when you think of a surface integral, you can think of it as a weighted surface area. You're really computing the surface area, but at every single point on that surface, you're going to weight the surface a little bit by whatever you want. If you want it to have a uniform weight, or maybe like a uniform density, right? Then you can just set it to be equal to 1 or 2 or just any constant. And then what you get is you just get the area. That's it. Pretty cool stuff. It's just such a natural generalization. It's very, very beautiful. All right, so we've got some examples to do, and I do want you to try to do these on your own first before we do them together. So I want you to first try to compute this surface integral, where S is the sphere of radius A. And just to emphasize what's going on here, you're integrating the function x squared, but the region over which you are integrating is the sphere. All right, so there's a distinction between the region that you were integrating over and how you describe that region and the function that you were actually integrating. In this case, the function is x squared. The region is the sphere. All right, so think about this one for a minute. First example of the day, right? So think about it. Then you know what to do next. You got to say something out loud. Doesn't matter if there's anybody around, just say it to yourself, say it to whatever, your phone if you want, your computer, just say something out loud. Okay, and now I want you to try to compute it. So try to compute this surface integral, and how you go about it, you have some options, but I think you can probably guess what a good way to start would be. All right, here we go. So because we're going to be integrating over a sphere, it's natural for us to choose spherical coordinates to do all this. So let's use the spherical parameterization of this region. Because the radius is fixed, the radius is a, we're going to get that for x, that for y, and that for z. Now we need to compute the partial derivatives. I'll leave it to you to compute those. We've done it a couple of times. We did it in the last section. Compute those partial derivatives. and then compute the cross product of those two partial derivative vectors, and you get this mess right here. This mess right here. Oh, shoot, hold on a second. Let me take a look at my camera. Give me one moment. Okay, hopefully that fixed it. Yeah, it's just time for me to get a new camera. Maybe I'll finish out this series of lectures, and then before I do the next ones, I'll get like a nice camera that's new, not several years old. Okay, where were we? That's right. Okay, so we just computed the cross product of those partial derivatives. Now we need to find the magnitude. So compute the magnitude of this cross product, and not surprisingly, this is the result we're going to get. Remember, this is the same thing we got when we used the change of variables formula, right? Remember, it was rho squared sine phi. That's what came out when you did the change of variables. So the same thing is kind of happening here. Now we have all the pieces, right? So if we want to integrate or do this surface integral, here is our function, but we got to convert everything to, well, what is x? X was that. And then we're converting ds to this. That is essentially us doing the change of variable right there, changing this to be in terms of phi and theta. Oops, there's a small typo. This should actually say phi, and that should say theta. There we go. I'll fix that after the recording. And now you've got an integral. So this we computed to be a squared sine phi, right? Or a squared sine phi? Yeah. Is that right? Yeah, that's right. So we can start pulling some things out and simplifying. At this point, you are just doing a double integral. So the technique is the same as what you remember back from section 15.2, 15.4, like any of those. You're just doing a double integral at this point. Take note of, oh, I think there's another typo here. Hang on, hang on. Yep, another typo. Sorry about that. This should be a phi, and this should be a phi also. Yeah, sorry about that. That should be a phi. That should be d phi. What I was going to say is that these two functions here, or sorry, maybe I'll say this. This and this are functions of phi, and this is a function of theta. So using that really satisfying corollary that we learned back in chapter 15, we can split this into two separate integrals and do it as a product of those two integrals right here. So my bad, that's kind of confusing. It's correct down here, but at this point, you're just doing integrals of a single variable. So just go through and compute those single variable integrals. And after you get through a little bit of work, you find that the final answer is 4/3 pi a to the fourth. And that's that surface integral. Okay, now just a quick touch on the physics applications. As you may suspect, surface integrals are ubiquitous in physics, and we're going to explore a few amazing ideas in the last two sections, 16.8 and 16.9. So for now, what we're going to do is we're just going to briefly point out the respective analogous formulas to those that we saw earlier a couple of times for like moments, center of mass. That's basically it. So here's how you do this. Imagine, for example, that you have a really thin sheet of some substance, maybe we'll say a thin sheet of graphene, and your graphene has the shape of a surface S. So you've got a really, really thin sheet, right? The density of the graphene is described by this function rho. So at any point on that surface, that's the thickness, or I shouldn't say the thickness, the density of the surface at that point, okay? Then the total mass of the sheet is going to be same thing we saw in the past. It's going to be density times ds, right? That'll give you the mass, the infinitesimal mass. You're going to add them all up, and that'll give you the total mass of the sheet. God, sorry, one second. My camera's like flashing and it's bugging me. Sorry, one more second. Okay, now I hope that worked for real this time. Okay, so where was I? We just talked about the mass. That's right. And so what is the center of mass? Well, the center of mass is going to be the same thing that you saw in the past. It's going to be the moment with respect to the various planes divided by the total mass. So this right here, this integral right here is the moment with respect to the yz plane. This here is the moment with respect to the xz plane. And this is the moment with respect to the, sorry, this is the moment with respect to the xy plane. And then you divide those all by the total mass, and that will give you the coordinates of the center of mass of the region. The moments of inertia can also be defined. You can find those in the textbook. We're not going to worry about them here. Just kind of a quick review of those, a quick update of those physics applications to surfaces instead of just regions. Okay, now let's look at surface integrals of graphs of two variable functions. So like we saw at the end of the previous section, any surface S that is given in this Cartesian form, where z is a function of x and y, you can describe it, excuse me, as a parametric function, or as a parametric surface with these equations, right? And now if you go through and you use the same kind of stuff we talked about already in the previous section, I mean, we already did this once before. These will be your partial derivatives with respect to x and y. This will be the cross product you get. That's going to be the outward normal vector. It's not unital, but it is the outward normal vector. And we saw that in the last section. Take the magnitude of it and you get this. And so now we're recovering that surface area formula, right? Same kind of thing. So the surface integral of a surface z equals g of xy, ooh, is this right? Yes, z equals g of xy is given by this formula right here. This formula right here. So again, yeah, this is just an application of the change variable formula, but also really think of the surface integral as like a weighted surface area, right? So before, if this was not here, you would just have the surface area, right? You just have the surface area. But now we want to apply a weight to that surface at every point. And the weight is given by that function f, this function f right here. So that's really what's going on. Okay, a natural corollary to all of this, if your surface is actually a piecewise smooth surface, so in other words, it's a finite union of smooth surfaces that only intersect on their boundary, then the surface integral over S is the sum of the surface integrals over all of the S sub i's. So just do the surface integral over this one, dot, 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 all the rest, and then you add up the results, and that will give you the total surface integral. Right, we're going to use this right now, actually. So this one may be a bit tricky, but I would like you to try this one on your own before we do it together. So I want you to try to evaluate the surface integral over this surface given here, and you're going to integrate the function z. So think about this for a minute. Okay, and now say something out loud about how you might begin. Right, and now try to work it out on your own. And one little tip I'll give you just as a reminder, remember the function you're integrating is z, but you're integrating over the surface S. So there's a difference between the function you are integrating and the region over which you are integrating. All right, here we go. So in our case, there are essentially three surfaces. There are three surfaces that we want to integrate over. One of them is this plane right here that you see on the top angled part. Man, it's hard to do that. Wait, no, this way. There it is. Okay, like that. There's also the surface that is like this cylindrical surface on the outer edges. And then there's also the bottom. So there's a bottom disk, and we need to integrate over that. So we have three separate surfaces over which to integrate. And what we need to do is we need to compute the outer normal vector for each one of those surfaces. That's the goal here. So let's focus on S1 first. Okay, so S1, oh wait, are we doing, hold on a sec. Yeah, we are, okay. So S1 is the sides of this figure that you can see here. And because this figure is naturally parameterized using cylindrical coordinates, we'll use cylindrical coordinates. So x equals cosine theta, y equals sine theta, and z is just equal to z. Cylindrical coordinates, right? In this case, the radius is 1. All right, theta is going to go from 0 to 2 pi. And now we can express z in terms of theta as well, because z is actually given by, wait, what am I? Hold on a second. What am I? Ooh, hang on a second here. Hold on, what am I saying this? Well, okay, so x is cosine theta. Oh, that's right. Yeah, that's right. Because I need the bounds. That's right. I need the bounds. That's why I'm doing this. Yeah. We need to specify what z is going to go between. That's what I'm doing right here. Just tripping myself out for a sec. So theta is going to go from 0 to 2 pi because we're going to do a full rotation. And z is going to go from down here in the plane up to that plane right there. That's the maximum height right there. And that height is going to be given by the function 1 plus cosine theta, because z is equal to 1 plus x. 1 plus x. That height right there. Okay, so now we have all the pieces. Now we need to compute the partials and take their cross product. So once you have these parametric equations, you can compute their partial derivatives, or the partial derivative of the vector function, cross them like we did before, and this is the cross product you get. Then you take the magnitude of that cross product, right? Square these and take the square root. This one happens to be very simple because cosine squared plus sine squared is 1. So we get 1 as this, this scaling, you could say. All right. Now we're going to plug all this stuff in and compute the surface integral on this vertical cylindrical piece. Here we go. So this is what we wanted to compute. We're reparameterizing it here in terms of this, like so. Z is the function that we are integrating, right? And we're integrating from 0 to 1 plus cosine theta, and then 0 to 2 pi. There it is. And then now we can go through and continue, right? So just apply FTC2 here, and you'll get this. And then now you've got an integral of a single variable. In this case, it's a trigonometric integral, so you can use techniques that you learned back in Calc 2. You're going to have to use the power reducing identity to get this term. And then this is the other term that you get just when you multiply this out. Then you've got simple integrals to evaluate, so you can run FTC2 again, plug those values in, simplify, do the arithmetic, and you get 3 pi over 2. So what we just discovered is that the surface integral over this cylindrical part of the surface ends up being 3 pi over 2, surface integral of the function z over this part. All right, now we have to go to the other surfaces. So let's go to S3. So just a reminder, S3 is this plane right here. S3 is this plane right here. Now we need to integrate over that region. So here we go. We know that it lies in the, oh, I'm sorry, I'm skipping ahead. Sorry, S2. Sorry, S2 is down here. So S2 is that disk, and that disk lies in the XY plane. So when we integrate this, oops, when we integrate Z over that disk, well, Z is equal to 0. Z is equal to 0 on the XY plane. So we're integrating the 0 function, and we're going to get 0. So there we go. That's that one. Now we're going to look at S3. My apologies for mixing that up. Now we're going to look at S3, which is this angled region right here. So on S3, we know Z equals 1 minus X. And what we can do is we can just use that formula from a previous corollary, because that one is just a function of X and Y, right? So if you think about that surface again, sorry, I know I keep going back and forth. This surface is really just a function of X and Y. It's like a plane, right? So we can just use that formula that we derived like so, just like so. Here's our function Z. The one thing you got to remember is that all of this is still in Cartesian coordinates. So this formula is true when your function is given in Cartesian coordinates. However, because of the region itself, notice the region is, it's like an ellipse right here, right? And the projection of it is a circle. So this suggests that we could use polar coordinates to evaluate our double integral, and it might be easier, much easier in some cases. So we're going to do that, convert everything to polar. 1 plus x becomes 1 plus r cosine theta. This we can compute directly. We just compute derivative of z with respect to x and y. You get this. And then we need this extra r since we're converting everything to polar. That's the idea. Okay, now what is left? So now simplifying and pulling some scalar constants or scalar multiples out, this becomes our integrand. And now we can do our integration. I think, what do I do here? Yeah, anti-differentiating with respect to r is pretty easy. So we can go ahead and compute this integral right away. And you'll get this after simplification. And then we can compute this integral with respect to theta. That one's also not too bad. And then simplify things, you get root 2 pi. Okay, so all together, 3 separate surface integrals all together. We're going to add them all up. This was the surface integral over the sides. This was the surface integral over the base. This was the surface integral over that planar region, this one, like right here. Add them all up and you get this. And there it is. All right, moving along. Now that we've seen how to compute surface integrals just for, surfaces described by vector functions, graphs of two variable functions of x and y, next we need to talk about orientable surfaces, because we can't talk about flux without talking about orientation to some degree. So in an earlier activity, in particular, the activity we already did for 16.6, you got to see your first example of a non-orientable surface, the Mobius strip. This is just a fun, funky surface. It's easy to make in real life. You just take a strip of paper and then you twist it and then glue the edges together and you'll have created a Mobius strip, just like so. Now, the catch about this particular object is that it is a non-orientable surface. And the reason is you can't define the notion of up and down in a well-defined way. And the easy way to think about it is if you were an ant crawling along this surface, well, at some point you're going to be on the bottom, but if you keep walking in a straight line, you will end up on the top. So let me kind of illustrate that here. Let's say we start right here, or here. Yeah, actually, let me try to draw it like so. So right at this point, let me zoom in. Here we go. Right at this point, we could choose let's say the normal vector is pointing this way. So we're going to say that is up. I don't know, like pretend you're like on your side, like walking along it, right? So that way is up, and that's up, and that's up, and that's up, and that's up, 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 right? Or out, see? It's very hard to draw. And now we're going to keep going around the back, right? And when we keep going around the back, now we're going to be pointing this way, this way, this way, this way, this way. So even though we walked all the way around, at this point, what was down, or sorry, what was up is now no longer up anymore, it's down. And we could have gone the other way. If we had started by pointing this way and then walked around, we would end up facing the opposite direction when we returned to that point. So this is a non-orientable surface. There's no way to define what is up and what is down on this surface. And if you try to, it doesn't work. All right. So that's really what we mean when we talk about an orientation or an orientable surface. We need to be able to rigorously define a direction, right? A direction. So here is how we do it. Suppose S is a surface that has a well-defined tangent plane at every point, except perhaps at some of the boundary points. If it is possible to choose a normal vector n at every point so that n varies continuously over S, then the surface is said to be orientable, and S is called an oriented surface. So in other words, if you can well define that normal vector, and that normal vector varies continuously, then you've got an orientable surface. And the choice of n provides you with what we call an orientation. Now, one thing about this to keep in mind is this first note. There are always two possible orientations for any orientable surface. And that's because at every point, you could either choose to go that way or that way. You could call this up or you could call that up. And it's the same thing we saw here. Right at the beginning, I had to make a choice and I said, oh, I'm going to call this up, right? Well, I could have done the opposite. I could have said, call that up. And that's the idea. So for any orientable surface, you've always got two choices of what up is. Yeah, and they're parallel, so they'll be parallel in either case. So from now on, so this is one nice thing, from now on, we are only going to consider orientable surfaces, in other words, two-sided surfaces. So we don't need to worry about the Mobius strip or anything like that. We're just going to assume everything is nice in the sense of orientability. Okay, I hope that makes sense. All right, now, if your surface is given as a function of x and y, then the surface has a natural orientation given by the outward unit normal vector n. So this one is actually a unit normal vector. If you remember from, oh geez, sorry, one second. If you remember from the previous lecture, and then also I think I said it earlier today, This will give you an outward normal vector, but it's not unital. So if you want to make this a unit vector, then you got to divide it by its length, and that's what the length is. So if you take this outward normal vector and you divide it by its length, you get an outward normal unit vector, and that's what we refer to when we write n. We're assuming it's unital. Yes, and since the k component here is positive, that's what's giving us the upward orientation of the surface. So again, we're talking about surfaces in terms of x and y. Up is what you would imagine. Up is up. Up is in the positive z direction, and that's what this is giving right here. All right. Now, if S is just a smooth orientable surface given by some vector function, then it's automatically supplied with the orientation of the unit normal vector given by this. There we go. So again, this is the normal vector. Dividing it by its length gives you a unit normal vector n. So this is like the general formula. This is the specific formula for functions of x and y. That's the basic idea. All right. So this is the general one. Okay. Now, oh shoot. Oh no, this is right. Yeah. So just to give you an example of computing this normal vector, if you remember back in example 1, we found that for a sphere of radius a, this cross product was given by this long mess. Right, and then we also found that the length of that vector is a squared sine phi, which agrees with what we would see from the spherical parameterization, right? Now, if we want to find a normal vector a unit, oh my gosh, a unit normal vector, we can just take this normal vector and divide it by its length to get a unit normal vector. Okay, I will leave you to do these calculations. They're not too hard to do, but just divide this by this, and you'll see that you end up getting this, which is nice because this is actually the same thing as the original spherical parameterization, but with a removed. So we divide it by a. So in other words, the outward unit normal vector to a sphere is given by this formula right here, right there. And this makes sense. This makes sense. So remember, this is the spherical parameterization of the sphere of radius a. And it makes sense that the normal vector would point in the same direction as the position vector. Just imagine a sphere, right? If you're on a sphere, the normal vector is going to point out like that in the direction of the position vector. So that's what's going on. You're seeing it manifest right here when we compute it using this more general theory, right? Maybe as a picture, this is what I'm talking about. There we go. So the position vector of a point on the sphere is given by, say, this, and we're saying that the normal vector, the outward normal vector, would be pointing in the same direction as the position vector. That's what this says. That's it. Now, if we had chosen the opposite, order of computing this cross product, then we would have gotten the inward unit normal vector when we went through all this stuff right here, and that would be pointing inward instead. There you go. And why is that? Because remember, when you switch the order of the cross product, you get the negative of that result. You get the negative of the original one, or you get the opposite of the result. All right. So now we can define what our closed surface is. So a closed surface is just a surface that is the boundary of a solid region. Easiest example is something like a sphere or just a blob in space. Just imagine like a blob in space. That blob has a surface, and we call it a closed surface. That's it. On these surfaces, the positive orientation points out, and the negative orientation points in, just like you see in these pictures. All right? Okay, now that is all we need to finally get to talk about flux. Yes, now we get to define flux. This is when things get really cool, I think, and just shows you how amazing the integral is and just how amazing mathematics can be to be able to describe these things so rigorously and intuitively. All right, here we go. So suppose that your surface S is an orientable surface with a unit normal vector n, and I want you to imagine a fluid with density rho, and a velocity field flowing through your surface. So this is a good picture. There's your surface S, and I want you to imagine a force field or a velocity field or a vector field flowing through the surface S. A really, really good thing to picture is imagine a fishing net across a stream. So just imagine you took that net and you flicked it down into the stream. The water is going to flow through the stream, right? The water is going to flow through the stream. That is the intuition that we're working with here. That's the basic idea. That's what it looks like here. Um, so what we're going to do is this, the rate of flow, that's mass per unit time, the rate of flow per unit area is rho times v. So density times that vector v. Now, here's the construction. Again, repeating this a whole bunch of times. Divide your surface S into a bunch of small patches. And then when these patches are very small, S sub ij is nearly planar. So when you make the patch small enough, because our surface is smooth, it's going to look like just a plane. And when you get smaller and smaller and smaller, they look more and more like a plane. So what we can do is we can approximate the mass of fluid per unit time crossing through that patch in the direction of the normal vector. All right? So this is the picture you want to think of, and this is what we're getting right here. So A of S sub ij, that's the area of this patch. And then what this is doing is this here is the rate of flow, and we're going to dot it with the normal vector. Dotting it with the normal vector basically tells us how much of it is aligned with the normal vector, right? It's that that dot product giving you that alignment measure. So that's what's happening here. We want to measure how aligned that flow is to the normal vector, and we're going to multiply by the area of the patch. Here we go. Summing up all of these values, taking the limit, making the partition more refined, yada, 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 you get this surface integral right here. So this dot n, and this is just writing everything out in terms of x, y, and z, in terms of our three coordinates, x, y, and z. One thing, this is a scalar multiplication, just to point out, and then this is a dot product. So this is a dot dotting these two vectors. So physically, what we're talking about, physically what this integral is giving you is the rate of flow through the surface S. It's basically how fast stuff is flowing through that surface. It's how fast the water is flowing through that fishing net. That's what you're getting with this integral. Now, we had originally defined this in terms of like a density, right? But we can do this more generally. We can consider this to just be any general vector field F, all right? So when we could just consider this for any general vector field F, our integral becomes this, that right there. And that, my friends, is flux. So that is the surface integral of F over a surface S. And that is how it works, and that is how it all comes together. So just to state it outright, if F is a continuous vector field defined over some oriented surface S with unit normal vector n, then the surface integral of F over S, otherwise known as the flux of F across S, is given by this integral right here. This integral right here. Super cool, just super cool stuff. And it makes sense, right? It just makes sense. Let me go to this slide. This makes a lot of sense when you think about the construction of the Riemann integral and you think about how this is working. What is F dot n? That is how much of the force is aligned with the outward normal vector, right? And we're going to multiply it by the infinitesimal area of that patch. And then we're going to add all of that up. That's what we're doing. So we're going to get the flux. That's what that says. Oftentimes, just for notational cuteness, we can rewrite this as this, F dot D of S. It's just literally like merging these two things together, treating this as like N times ds. That's what's going on right here. So that's another way of expressing it. But so just to reiterate, flux is essentially the speed of stuff passing through or acting on a surface at any single moment in time. Any single moment in time, it's going to be like, psh, okay? Naturally, the flux is the greatest when our surface is perpendicular to the flow of the field. So again, think about the fishing net example, right? If you've got a fishing net here, I can't really do it. If you've got a fishing net like this, right? Then the flux is going to be the greatest when the vector field is flowing like perpendicularly to the sheet or to the net, sorry, right? Just like so. So flux will be the greatest when that's the case. The flux will be the least when the surface is parallel to the flow of the field. So when it's parallel, you're not really passing through the net, right? You're passing like along the net, but you're not passing through it. That's what it is. So this is when the flux will be the least. This is when it will be the most. This is when it will be the least. And what's really, really cool about this, I mentioned this a moment ago, but just notice how that relationship is captured by the dot product. That's why the dot product is such a critically important thing. The dot product is telling you how aligned these two vectors are. And we really, really need to know that. We really, really need to know how aligned these two things are, because now we can talk about things like this. We can say, oh, the dot product is going to pick out that if they are orthogonal, the flux is going to be big. But if they're parallel, the flux is going to be small, right? It's going to be zero. So yeah, cool stuff. Okay. Um, now what are we going to do? So if we wanted to describe the flux in terms of our parameter domain, we can. We're just going to do some calculations and get another version of this formula. So suppose your surface is described by this vector function. And we're just going to go through the motions and simplify things, right? So this integral you can rewrite as this. That's the surface integral, the flux. Now, what is n? Remember, n is the outward normal unit vector, which is given by this expression right here. There it is. Okay, but now what we can do is we can plug in this parameterization of the surface, right? So here we go. We're going to evaluate f on the surface and keep this the way it is. And then ds is just equal to this times dA, right? That's like this is the scalar for the area form to keep the value of the integral equal, right? That's the change of variable formula. But then what happens is something nice. These two values cancel out. And what you're left with is f dot this cross product and then dA. So it kind of simplifies things a bit. There it is. And then we get this corollary. The flux of a continuous vector field F through the surface R of u comma v defined on a parameter domain D is given by this formula. So if you want to integrate with respect to your parameter domain, you can. Or you can integrate with respect to the surface area of the surface. You can do that too. Right. Now let's do an example. Okay. Yes, okay. So this one I do want you to try on your own also. So I want you to try to find the flux of the vector field given by this function across the unit sphere. So very realistically, just imagine for a minute that you've got fluid, you've got like a spherical net, right? A spherical net, and you've got fluid flowing through that net. And the description of that flow is given by this vector field right here. And I want you to find the flux of that field over the unit sphere, okay? All right, here we go. So think about it for a minute. Okay, now say something out loud. Give yourself that verbal feedback. Give your brain that verbal feedback so that it knows what it's thinking about. Right? And now try to work it out on your own. You're computing an integral. You should end up with a number at the end. And that's all I'll say. There we go. Okay, now let's work on it together. So again, naturally, if we're talking about a sphere, we should use spherical coordinates. Let's use those parameters in this case again. So here is our vector function for the surface. The surface is given by this vector function. And here phi goes from 0 to pi, theta goes from 0 to 2 pi, and so on. It's the unit sphere, so there is no rho, or I should say rho is equal to 1. And then what we're going to do is we're going to evaluate our vector field on that surface. Hold on a sec. There you go. Hopefully everyone's all right. Okay, so where were we? Oh yeah, we're evaluating that force field, that vector field on our surface. So we're plugging in those component functions where they correspond here. Let me kind of like walk you through it for a minute. Z is equal to cosine phi when we're on our surface. So that's why cosine phi is appearing here. Y is equal to sine phi sine theta on our surface. So that's why this is appearing here. And then X is sine phi cosine theta on our surface. And so that's why this is appearing here. That's essentially what we're doing. So we're just evaluating the force field on the surface, and now we get this new vector function here. We computed this cross product earlier, so I won't do it again, but you're going to take this vector and dot it with this cross product. That's the normal vector, right? That's the outward normal vector, and you get this big mess. There we go. Okay. Now, don't let it overwhelm you. Just take things piece by piece. You can do it. Here we go. We need to compute this integral. There it is. Uh, we've already included our parameterization, so we just need to sub everything in and then go for it. Here we go. So this is pretty messy, but don't let this overwhelm you. Just look at the pieces, piece by piece, pull apart what you can, and then you're just going to have a bunch of trig integrals. That's really what it boils down to. So what did I do first here? Looks like I split it into two separate integrals, right? Yep. Did I? Um, did I? I did. Okay. Now I can see it. Sorry. So here is the first term. So I was doing this double integral here, and that's what's expressed right here. Okay. Now I was able to split that into a product of two integrals because this function is only in terms of theta, and this function is only in terms of phi. So that's why I've got these two integrals, and I'm taking their product, just like so. Right? Then I've got this other integral right here, and same thing here, I can split it into a product of two integrals because this is only a function of phi, and this is a function of theta, so I can split it like so. Now, oh yeah. This is actually going to become 0. That's going to cancel out because this integral will be 0. Yeah, if you integrate the cosine function over the entire interval, 0 to 2 pi, half of it is going to be negative, half of it is going to be positive, so they're going to cancel out, and this just completely goes away. Hooray! Thank you, even functions over this interval, I should say, or just thank you, cosine function for being even and periodic. So now all we're left with are these two integrals, and these ones we actually computed earlier as well, so we don't need to redo those calculations, and you should get 4 pi over 3 in the end. That's it. Cool stuff. Okay, now let's do another oh, wait, sorry. Oh, continuing. Oh yeah. Just to hammer home what is going on here. What is this value? So physically, this value means that at any point in time, this is how fast stuff is flowing through that unit sphere. That's what's going on. So if you look at this picture, at any moment in time, stuff is flowing through that sphere at that speed, 4 pi over 3. 4 pi over 3. That's it. That's the basic idea. So this is important if you really need to think about capacitance in some sense, right? Like, oh, I need things not to be flowing through here too fast. So how fast are things going to be flowing through here? Do I need to change something so that my system can actually handle that speed, or am I good? This is why we need this type of technology, this type of mathematical technology. All right. Um, Naturally, if our surface is given by a function in terms of x and y, we can reformulate all of these formulas to be in terms of x's and y's, and sometimes we get something nice. So here we go. If our graph is a function z equals g of x comma y, then when we do this dot product, we're doing this right here. Remember, this is the outward normal vector. That's what this is, right? So when you dot these, you're going to end up with this expression. And so we can re-express our integral like so. This is now going to become this. You don't need to memorize that. I think you should memorize this. You should definitely memorize the formula for flux. Hopefully it's not too hard to remember if you just remember the construction. Force field, dot it with the normal vector, the unit normal vector, multiply by the surface area form, and that's it. A little note here, we're going to use this in the next example. But also we're going to use this formula in section 16.9 when we prove the divergence theorem. Yeah, when we prove that, we're going to come back to this formula. All right, so with this formula in mind, let's take a look at this example. I want you to do this one on your own. Evaluate this surface integral, where this is your force field, and S is the boundary of the solid region E enclosed by the paraboloid here, and the plane Z equals 0. All right, so this one may take a little bit of thinking. So do think about it for a minute. Ponder it, think about it. Okay, now start by saying something out loud, just to give your brain that feedback, maybe what you would do first, right? And now try to work it out on your own, and we'll compare our answers in just a minute. Okay, here we go. All right, so let's see. First thing, well, we have our force field, we have our vector function there. We need to find a way to describe the surface itself. So the surface is the boundary of the solid region E enclosed by this paraboloid and this plane. So really we've got like the surface of a paraboloid, and this one is going to be opening downward and opening toward the XY plane. So what it should look like is something like this, and then that. There we go. Yeah, like that, just like that. So that's what our surface looks like. And we need to compute the surface integral over that surface where this is our vector field. Okay, so here's a better picture of it. And yeah, exactly. So by convention, we're going to have to orient it in the outward direction. So this is something you have to think about when you're computing these surface integrals. You have to compute an outward normal vector, right? So for example, like this is the outward normal vector for the parabola or paraboloid, right? Down here, this is the outward normal vector for the base, right? It's pointing outward. So you've got the outward normal here, the outward normal here, and then maybe the Squidward normal here. No, I'm just kidding. There we go. So remember, you got to think about which way is out. Which way is out. And let's see. Yeah, we're going to do two separate integrals here. Here we go. So we're going to use that formula that we just derived, where d is the unit disk. And the reason we're doing that is because you can describe this disk as a function of x and y, right? So here we go. In that case, wait, see, I should have copied the formula down. Okay, well, using that formula, this is P, this is Q, and this is, wait a minute, what am I doing? Oh, my apologies. Yeah, I'm sorry. We're doing the surface integral for the parabolic cap first. That's what's going on here, the parabolic cap. So uh, this is y, this is x, and this is z. So those are our component functions, just like that. Compute the partial of z with respect to x, partial of z with respect to y, and then we can use that formula. Here it is. So it was this formula. Oop, there's a typo there. This should say dot ds, dot ds. Okay, this is the formula. So just plugging in all those values gives us this right here. Okay, simplifying, we get this integrand here in terms of x's and y's. Now, because the region, or the region that we're integrating over is a disk, it's easier to use polar coordinates in this case. So we're going to convert all of this to polar coordinates and then iterate the integration process like so. So once you go through, remember like x is r cosine theta, y is r sine theta, so you get this. X squared minus y squared, or really, I should say negative x squared plus y squared, that's r squared. There it is. You got your r, because we're converting everything to polar, and then you get this big mess. And remember, don't let it overwhelm you. Just take a deep breath and just release any of that tension. Just go step by step. Things get messy, but they also get cleaned up, right? So go through this. Integrating or anti-differentiating with respect to r is not so bad. You get this. Luckily, the lower bound is 0, so it's going to wipe out a whole extra set of terms. And now we're back to a good old single variable integral. Single variable integral, just like you saw back in Calc 1 and Calc 2. Boom. Go through and finish, and you'll get pi over 2. So that's the surface integral over that parabolic cap. Now we need to do the surface integral over the disk itself. So the disk S2 is oriented downward. That's the outward normal vector, right? So the outward normal unit vector is negative k, that just straight up, I mean, straight down, I should say. I was going to say straight up down, but straight down. There you go, straight down. Okay, ooh, another dot missing right there. Um, Yes, okay, so now when we dot our vector field with our outward unit normal vector, we get something pretty quick and easy, something nice. We just get negative z. But again, on that disk that lies in the xy plane, z is equal to 0. So this just becomes 0. Integral of the 0 function is 0 over this closed region, and so we get 0. Altogether, the total flux is 0 plus pi over 2, which is pi over 2. So that's how fast stuff is flowing through that closed parabolic cap at any given moment. All right. So on that note, what we can do is we can talk briefly about electrostatics and heat flow. So this is the type of stuff that all y'all are going to see later on in your major courses, or maybe you're already seeing them in your major courses. This is a lot of the reason why this particular mathematics was developed. So physicists really needed to explore electrostatics and heat flow in a more rigorous way. And so they started developing the mathematics to do so. And that's what kind of birthed all of these ideas, right? Um, so this stuff, the mathematics can be generalized, but the applications are well known. They're well known and well used. So there you go. In general, the theory has been developed for general vector fields, but physicists and engineers and so on have very, very specific vector fields they want to use this on, and that's what they do. So for example, if your force field is an electric field, then the surface integral of that electric field is what's called the electric flux of E through that surface S. So that's the flux. And then Gauss's law says that the total net charge enclosed by a closed surface S is given by epsilon naught times the flux, like so. Like I mentioned, oh geez, I don't remember, many lectures ago, I don't remember. This is just a constant related to the permittivity of free space, like how much stuff is allowed to move because of the space you're in. And it kind of depends on the units. In the SI system, this value is approximately this, but that's the basic idea. Another application, so there's an electrostatics application. Another one is heat flow. And this one is studied tremendously. It's studied a lot. And for any of you that take a course in differential equations, you will be studying this particular equation, the heat equation. This is basically what we call the heat equation. So suppose that the temperature at any point in a body is given by the function u of x, y, z, then the heat flow is defined as this vector field, right? So remember, this is the gradient of u, and k is some scalar, and we choose the negative direction so that oh geez, what is it? So that it's to agree with the intuition of the way the heat is flowing. That's what it is. K is usually experimentally determined, and it has to do with the conductivity of the substance. And then the rate of heat flow across the surface is given by this double integral here, the surface integral. Now, here's where I'm actually going to show you this. I showed you this once before back in chapter 14, I think, but just a reminder about this PDE book, right? Right, Lawrence Evans's PDE book. I showed you this page way back then, and now what I want to do is show it to you again because you're going to be able to recognize some of these symbols now that you couldn't before. So here we go. I apologize. All right, see if I can do this. Okay, first, take a look at this. Oh, wait, what am I doing here? Hold on. Hang on. Take a look at this. Okay, where'd you go? Right here. That first integral right there. Give it a second. Ah, ah, can't see it. Anyway, wait, do I have autofocus turned off? Hold on, give me a moment. Just a second. I do. There we go. All right. Boop. There it is. Okay, so take a look at this thing for just a minute, right? That's a surface integral. That's a surface integral. F is the vector field. That nu, that's the Greek letter nu, that's your outward unit normal vector, and you're dotting F with nu and integrating with respect to the surface area. And look at the symbol that they're using for the surface. It's partial V, because this is the boundary of some region V. So now you can make sense of this entire symbol, and this is saying that this is equal to 0. Now down here at the bottom, check this out. That is the heat equation right there. That's what that is, right? That's the same thing we were just looking at, except they're using A instead of K, and D represents the gradient, and U is our function U. There you go. Oh yeah, and see it even says at the bottom there, the minus sign, right here at the bottom, these things. Oh wait, no, sorry, that's this one right here. Wait, equation 2. Oh yeah, yeah, don't worry about that. There you go. So you're getting to get to see it all, right? You'll get to see it all again. You're seeing it now. You're learning all of the tools, all the techniques, all of that stuff. So that's why Calc 3 is fun. Okay, total tangent. Give me a minute. Let's get back to things. Oh, let me turn off autofocus too. Here we go. Okay, back to the slides. All right, so just quick examples of electrostatics and heat flow. You'll explore them in more detail later. All right, so now let's try this example. This one, yeah, you all can try this one on your own too. So here it is. The temperature U in a metal ball is proportional to the square of the distance from the center of the ball. Find the rate of heat flow across the sphere S of radius A with the center of the ball. Okay, so ponder that one for a minute. Okay, now talk to yourself or talk to your friends. Say something about what you might be able to do. Try to make some sense of the problem. And then try to work it out on your own, and we'll do it together in a moment. Okay. Okay. Yes. Okay, here we go. All right, so for ease, we're just going to take the center of the ball to be the origin. So let's just make it easy on ourselves. We don't need to move the center anywhere else. Then we are given that the temperature is proportional to the square of the distance. So that means that our function here, our temperature function, is just some constant times the distance from the origin squared, which is this, which gives us that. There we go. So then the heat flow is given by this here, the heat equation, right? So the heat flow is given by this. We need to compute the gradient of this function, which is this. And we're going to multiply that by negative kc. Factor out a 2, and we get something a little bit simpler. So that is what our vector field looks like, our heat flow field. Okay, now at this point, we could use the standard spherical parameterization and find the normal vector by computing a cross product as before and so on. But we already determined that the outward unit normal to the sphere of radius A is in the direction of the position vector, right? It's in the direction of the position vector. You just got to divide by the radius itself. So we already know what this vector is going to be. It's going to be 1 over A times the position vector for any point on the sphere. So we don't need to repeat that process. We can actually use our intuition in this case to get this, even though we justified it earlier too, so it's not cheating in that sense. Okay, now we can compute our surface integral. F dot n is going to be this. There we go. So we're dotting it with n. That's where the 1 over a and this comes from, right? Yeah. And then we simplify things because x squared plus y squared plus z squared, that's equal to a squared because we're on that surface. So it's going to be equal to a squared. One of these will cancel, and then this is what we're left with. So that is the function f dot n. That's what we're getting, and it's just a constant in this case. So then what is the rate of heat flow? We're going to compute our surface integral like so. Luckily, this is a very easy one, because again, if we're computing this integral, this is just going to give us the surface area, right? The surface area of whatever the surface is. So it's this value times the surface area. The surface area of a sphere is pi, or 4 pi r squared. In this case, r is a. So we get 4 pi a squared. Mush everything together, combine like factors, recount a little bit, and you get that. There it is. So that is the rate of heat flow across the unit sphere. How cool? How cool is that, right? All right. On that note, let's play. So we're getting close to the end here. I'm excited to do this activity with you in class as well. I hope you can see that surface integrals are just really, really powerful tools, and they're just really fun to play with. The mathematics of how they work is just so beautiful and elegant. I hope you enjoy it. I won't ramble on too much longer. We've only got two more sections left, 16.8, which is on Stokes' theorem, 16.9, which is on the divergence theorem, and then that's going to round out Calculus 3. So I will see you next time. Thank you all again for watching and listening, and have a good one.